So we will continue with the concurrency control protocols, as we have already seen many protocols, locks and timestamp based ordering protocol and so on, also the multiple granularity lockings. But if you have noticed, in all of them there is one recurring problem, which is the deadlock. So most protocols can fall into this trap of deadlock. So the basic the basic 2PL protocol can fall in the trap of deadlock, but the timestamp ordering protocols cannot, of course, but the locking protocols can always go into this deadlock state. So next what we will be studying is to see how to handle this deadlock. So the first thing is the deadlock prevention that we will study. So what I mean by deadlock prevention is that this type of schemes, the deadlock prevention schemes, never allow a system to enter into a deadlock. So they never allow deadlock. So if these schemes are run, the system will never deadlock. So we have already seen an example of this. The timestamp based ordering protocols are, of course, deadlock prevention schemes. So the timestamp based, the protocols that use the timestamp, the basic timestamp ordering protocol and the validation based protocol, they are we have seen that these are these deadlock prevention schemes because they never allow deadlock. Then there are two, so what happens in that is that, so in these deadlock prevention schemes is essentially in the timestamp based ordering protocols, what happens is that when a transaction or when an operation of a transaction appears out of order, then one of them must roll back. If you remember in the read timestamp, while we were checking the read timestamp and the write timestamp, there are two ways. We said either the transaction T that is trying to write it should roll back, or the transaction T1 or T2 for which it is not correct should roll back. So now, so which one should roll back? That is a question. So is it T or is it T1 or T2? That's the thing. So for that, there are these two schemes. So the first one is called a wait die scheme. In the wait die scheme, this is a non-preemptive scheme, and we will see what does a non-preemptive mean, but just remember for the time being that this is a non-preemptive scheme. Okay, what happens is that here the older transactions wait for newer transactions. Okay, so suppose there is an old transaction T1 that wants a particular lock on an item X, and T2 which is a younger transaction. So T1 is old and T2 is young. T1 is currently holding that lock. So then the older transaction simply waits for the young one to finish. So the old waits, that is fine. So if the older comes after the younger and the T2 is already holding the lock and the older one wants to wait, it just waits. Okay, fine. The younger ones, however, do not wait. If a younger transaction wants this thing, wants a lock, they simply roll back. So that means the younger ones do not wait for the older one. So if the younger one comes and sees that an older one is already holding the lock, it simply dies. So that is why it is the thing. So this is what is happening. So the younger one, young one is holding, is waiting for a lock. It doesn't wait for a lock, it essentially just dies because an older transaction is currently holding the lock. So this is why it is dies. It just rolls back or aborts, which is the same as abort. So that means it's dies, and this is why this is called a wait die scheme. So this is the thing, and the younger ones, as you can see, can die many times, because what happens is that when a transaction rolls back or dies or aborts, whatever is the terminology, it restarts with a new timestamp. So when a young one restarts, it restarts with, of course, a younger timestamp. So the chance that it will die again is more. So it can just keep on dying again and again. And this is called a non-preemptive because nobody removes any other transaction. So the old transaction simply waits for the young one to finish, and the young one simply dies. So nobody preempts another transaction. So nobody hurriedly removes another transaction. So that is why this is called a wait die transaction. Okay. So the other thing in this is the wound wait scheme. This is preemptive. And again we will see what does preemptive mean later, but let us see what happens. Is that the older transactions kill newer ones. So this is interesting. So kill young transactions. Okay. Now what does this mean? So that means that suppose there is a young transaction T1 which is holding the data item X, and a old transaction T2 wants the data item X. So at that point, since the old transaction has come, the young is holding to it. The young is made to release the lock, and the young is essentially it dies. So the young one dies, and the old one essentially now gets the lock and continues with this. So the young one is made to die. So that is why older transactions kill young ones. Okay, that's the thing. And what happens to the younger ones? The younger ones simply waits. So an old transaction is holding the lock, and a young transaction comes, it simply waits. So the younger one is simply waiting. So in the terminology, the old one is said to wound the young one. So it stabs the young one, it kills the young one, whatever is it. That is why it calls, and the younger one dies. So this is, it wounds it. So that is why it calls a wound wait protocol. Now this is preemptive. Why is this preemptive? Because when an older one comes and it sees it wants a lock which is held by a young one, it preempts the young one. It forcibly aborts the young one. It forcibly removes the lock from the, it forcibly makes the younger one unlock it. So it removes the named data item, whatever the data item, from the young one. It makes it release it, and it preemptively grabs the data item, even though the old was holding it. So that is why this is a preemptive data item. Now transactions, in this case what may happen is that transactions may be started with the same timestamp. So transactions are restarted, it may be restarted with a younger timestamp, with a new timestamp, or restarted with the same timestamp. So this is the other thing. Now one can show that there is no starvation in this scheme. There is no starvation. Why is that? If the transactions are restarted with the same timestamps, why is that? Is that at some point in time, if the starvation, when does starvation happen? Is that, remember that when a transaction wants a data item and it cannot get it, the next time it wants it, by that time some other transactions have got it, and so on and so forth. Now if a transaction is restarted and it is restarted with the same data item, at some point in time this transaction must be the oldest one that is around, because every other one has got it, and so on. So every other older transaction has finished, and this is what is being starved. So then it will be getting it. It will wound all the young ones, and it will getting it. So there will be no starvation. On the other hand, the same thing happens for the wait die is that at some point in time this transaction must be the oldest one. So it must simply get it, because it will wait for the young ones to finish, and another transaction which is also wants it will not be getting it because it is younger than this. So this is the older one. So then it will get it. So there is no starvation, and as we have already understood that there will be no deadlock. So this is free from starvation, and this is free from deadlock. Now among these two things, which is the better one? As it happens that in the wait die transaction, the young ones keeps on dying, because every time it is restarted there is some old one that is being done. So it's a young one reaches to this place where the old one is already holding the lock, and it dies. It restarts and it reaches the same place and it dies. So it keeps on happening. So it dies many times. So in that case, essentially the wound wait has more rollback. So the wound wait protocol, the wound wait scheme rather, has more rollbacks than the wait die scheme. So among the two things, the wait die is preferred. Okay. So between the two schemes, the wait die and wound wait, the question is which one is more preferable. Now what happens in the wait die is that the young transactions may die many times. Now what does it happen is that when a young transaction reaches to a point where it wants a lock, it looks for an old, it sees that there is an old transaction that is holding to it, so it dies. Okay, fine, and it is restarted. By the time it restarts and reaches the same point, it may be happening that the old transaction is again holding it, so it again dies, but the chances of that the old transaction finishing is larger. That is in the wait die. In the wound wait, what happens is that the wound wait, the older transactions kill the younger ones. So if an old transaction, some very old transaction that was supposed to happen much earlier comes, it will kill all the young ones. So even though the younger transactions die many more times in a wait die, an older transaction may kill more transactions in a wound wait. So in general, wound wait has more rollbacks. So what is preferred is the wait die scheme. Okay, so this is about the deadlock prevention. We can also talk something about deadlock recovery. So deadlock prevention schemes will never go into deadlock, so there is no question of recovery, but these locking schemes, they are not deadlock prevention schemes, so they may go into deadlock. Now the question is, once a system goes into deadlock, it must be detected and it must be recovered. So the system must not keep on waiting, of course, it must be, the deadlock must be broken. So how is the way to be done? So the first thing to recover from a deadlock is to identify the deadlock. So that is called a deadlock detection. So how is a deadlock detected? This is very similar to some concept that we did earlier. Anyway, so the concept that it uses is something called a wait for graph. Okay, so this is a wait for graph, and we in the conflict serializability we saw a graph. This is kind of the same thing, and what happens is that in this wait for graph, suppose Ti waits for Tj. Okay, that what does this mean? That Ti waits for Tj is that Tj is holding a lock on an item that Ti wants. So then in the graph, so the graph, the nodes are transactions and the edges are according to this wait for things. So the edges are the waits for relationships. So in the above case, when Ti waits for Tj, there will be a node Ti, then it will have a directed edge to a node Tj. Okay. Now what happens in a deadlock is that Ti waits for Tj, then Tj waits for Tk, then Tk waits for something else, and finally that something else waits for Ti. That is why it is a deadlock. So now you can clearly see what is going to happen in this graph is that now Tj waits for Tk, then Tk waits for something else, then something else, then that waits for Ti. So that is what does that mean is that for this graph to say whether there is a deadlock or not, there must be a cycle in the graph. So only when there is a cycle in the graph, it can be detected that there is a deadlock. So how does one detect if there is a cycle in this directed graph? This is the same as we did in earlier in the conflict serializability graph, etc. So one can run a depth first algorithm to find out if there is a graph. If there is a cycle, then there is a deadlock, because in that cycle all the transactions are waiting in a circular manner. If there is no cycle on the other hand, then there is no deadlock. So it is this thing.